Hello, I'm Nihaanth reddy vulupala. This is my final project for CAP6415 computer vision. Today I'll be demonstrating my project, a comprehensive comparison of state-of-the-art small neural networks. The main problem of this project addressing is that how do we select optimal neural network architecture for resourceful constrained edge devices. While many small neural networks are designed for efficiency and the relative performance across diverse datasets will not well understood. So this is my GitHub repository. I'm following the I'm following the naming convention of CAP64 Financial Year 2025 Project SOTA State of the Art Small Neural Network Comparison. So this is the readme file and these are the file structures I am following. And so we are comparing four neural networks models in here. MobileNet v3 small model of 2.5 million parameters, EffectiveNet b0 5 million parameters, ShuffleNet v2 version 2 of 1.4 million parameters, SquareNet 1.1 with 1.2 million parameters. And so across these things we are using three datasets: Cipher 100, Stanford Docs, and Flowers 102. So the model selection is we did based on an important note here is that while the project requires small neural networks model with less than 50 layers, I have included EffectiveNet B3, which has a little bit more architecture, but it is less than 5 million parameters only. And the key point of this layer count alone doesn't determine the network size. The type of operations and parameters count are equally important metrics. All models are designed specifically for resource constraint deployment, which is focusing on their comparison. The for dataset I deliberately choose three different datasets from Stanford ImageNet benchmarks. This is not recreated of any publication reader results. Instead, I have evaluating this transfer learning effectiveness from ImageNet to Cipher 100 for low resolution general objects, Stanford Dog for fine grained breed classification, Flowers 102 for limited training data scenarios. So let me show you the project structure. So as we discussed earlier, the data I just wanted to show you the dataset. These are the three datasets I've been using for this project to comparison. So the model, this is the project structure: train.py, evaluate.py, visual results.py, models, and this is the overall project structure. And train.py is the main training pipeline. Evaluate.py is the comprehensive evaluation script where all the basic evaluation happens between the models compared with different datasets. This is the train.py. This is a well structured and documented code. So I documented everything, early stopping to avoid overfitting and all. And this is training on epoch. After training one epoch, it will store in the logs by returning epoch loss and epoch accuracy. This is the validation code. Save checkpoints, training arguments, and as you can see, this is the well documented code. And next, evaluate.py. See, this is the evaluate.py. This is the well documented code. Evaluate model's accuracy on test set. So this is returning the accuracy, measuring the inference time. As you can see, this is also a well structured code, and this is for models.py. We are using all four model implementations in here. See, get efficient net, get mobile net version 3, get stuffle net, and get squeeze net. So this init.py is used for getting the model from the cloud or Kaggle. And utils, next we are going to explore utils library. Utils directory had data loader and helper functions. This is the data loader. In this function we are loading the dataset, the three different dataset we are using, and splitting into test, train, validation dataset equally. So this is the config yarml file. This is where we are setting hyperparameters and settings of the model we are using. So as you can see, these are the dataset, these are the training, early stopping, arguments, model configurations, evaluation and visualization. And next we are going to look into checkpoints. As we can see, based on these are the saved model weights for all 12 experiments. So we are using 3 models and 3 data sets and 4 models. So that is 3 into 4, that is 12 experiments in total. And these are the weights of the model we are looking into it. These are stored in checkpoints. And next we will go into result where we are storing all the figures and everything. This is where we are seeing the evaluation result and visualization of the model. So next we'll go into checkpoints. Not checkpoints, sorry, logs. So this is where we are storing logs for past 5 weeks, week 1, week 2, week 3 and week 5. These are the development blocks. I have maintained weekly development logs documenting my progress from 1 week to week 5. And week 5 focuses on comprehensive code documentation and visualization creation for this demo. And next we are going to go to terminal and try we are going to learn more about the code we used. Like I used train.py. In train.py we can see what each function does, the algorithm or the process used, the parameter description and return values. For example, in this one, in train one epoch, we can see this function is completely documented for forward pass, back propagation and gradient update. And early stopping class. Early stopping class includes detailed comments explaining the overfitting prevention mechanism and how patients work. And in models init.py In models in a.py, this is a comprehensive documentation of all four architectures, explaining their unique design principles. Each model loads explains the architecture feature, mobile V3 inverted residue effect, efficient nets, compound scaling, shuffle and squeeze net fire modules. So these are discussed in this models init.py, and next we will look into attributes. All the code is properly attributed from original authors. The model section cites the original papers ModelNet V3 from ICCV 2019, EffectiveNet from ICML 2019, ShuffleNet version 2 from ECCV 2018, and SqueezeNet from 2016. I acknowledge that this is the official PyTorch official models and TIM library for the implementation. Now we are going to set up the model. Now I'll demonstrate the code execution. First, let me activate the virtual environment is already activated. I'm using Python PyTorch and all the dependency installed from requirement.txt files, and I've already trained all the 12 models. Each training time took around 30 to 40 minutes for 15 epochs. The checkpoints are saved in the checkpoint directory. You will see all the 12 models are present. Now I'll run a comprehensive evaluation script that tests all 12 training models and the respective test set, measuring accuracy, inference time, and model size. Now we are going to run python evaluate.py. As you can see, it's loading each model, running inference on test set and measuring performance. See. So as you can see, the evaluation has completed, and let me walk you through the results. We evaluated all the 12 combinations of 4 models across 3 datasets. So best performer, first looking at the best performer, MobileNet V version 3 achieved the highest accuracy on Cypher 100 at 79.26 and 86.16%. On Flower 102, EffectiveNet achieved on best result on fine grained classification task 89.4 on Flowers 109 and 71.02 on Stanford Dogs dataset. So notice the trade-off between the model size and accuracy. Achieves 79%. MobileNet V2 is only 6.2 megabytes, achieves 79% accuracy, while EffectiveNet is 15.78 megabytes, but achieves higher accuracy on fine-grained tasks. This demonstrates us that EffectiveNet and efficiency on MobileNet version 3 for resource constraints deployment. Inference time, looking at the inference time, MobileNet version 3 averages around 13 milliseconds per batch on Stanford Dog and Flowers 102, making it suitable for real-time applications. EffectiveNet is slower, taking up to 238 milliseconds on Cypher 100, but still acceptable for server deployment. And there are two noticeable failures here. SufferNet and SqueezeNet both performed very poorly on Flower 102, only 10.29% and 2.37% accuracy respectively. This suggests that these are extremely lightweight models struggling with small datasets that have limited training samples. Flower 102 had only about 8,000 images, which isn't enough for this minimal architecture to learn effectively. Consistency. Model V3 shows that most consistent performance across all the three datasets. Mostly is a reliable choice for diverse deployments in our scenarios. And here we can see the JSON file. This includes including test accuracy. This JSON file includes test accuracy, model parameters, size in megabytes, inference time for each experiment. This data is used to generate our visualizations. So summarizing each model: MobileNet version 3 best model, high accuracy with small size; EffectiveNet highest accuracy on fine-grained tasks but larger and slower; ShuffleNet smallest model but struggling significantly with accuracy. Model performance: QuizNet moderate performance but fail completely on Flower 102. So next we are going to evaluate the results. So the evaluation is successfully completed. Now let me show you the results. So this is a JSON file. Model, test accuracy. These are all the 12 experiments for now. And next let us visualize the results. So these are the results. So these are the basic visualizations. As you can see, on Flower 102 dataset, ModelNet version 3 is second, EffectiveNet is the highest, and these two are very poor performance. On CipherNet, EffectiveNet v3 is more, and EffectiveNet is 65, and the third is, so this is the second, SqueezeNet is second, and ShuffleNet is the last. On Stanford Doc, EffectiveNet is highest, 71.1% of test accuracy scores, and MobileNet version 3 with 63.1% accuracy, and third is QuizNet and ShuffleNet. So this is the side versus accuracy comparison. As you can see, on MobileNet v3 is Cypher 100. Model size is in x-axis and test accuracy is in y-axis. As you can see that EffectiveNet has the highest model size, which is around 16 MB, and the accuracy is also higher. This is for each dataset: triangle, rectangle and circle is for CipherNet, and other two are for other two data sets. And this is the inference time. EffectiveNet is highest on Cypher 100 dataset, which took around 245 milliseconds per batch. And other two, we can see it's been running very fastly on the other three models. These are the results. Model comparison summary. As you can see, the accuracy, model dataset accuracy, test accuracy, parameters, size and time taken in milliseconds. Based on these visualizations, MobileNet V3 offers best overall balance with 79% accuracy on Cipher 100 with only 6 MB and fast inference. This is the best choice for mobile and edge devices. Next, Efficient Net achieves the highest accuracy on fine-grained tasks like Flower 109 at 89% but requires 15 MB. Best for cloud and server deployments where accuracy is critical. Next, ShuffleNet version 2 is the smallest and at only 1.7 MB and fastest at 14 milliseconds, but accuracy suffers significantly on complex datasets. Only suitable for small tasks on very constrained IoT devices. SqueezeNet completely failed on Flower 101 with only 2.95% accuracy, showing that aggressive parameter reduction has limitations. Benefited from longer training, that 2.95% accuracy suggests that model failed at early training phase. We can look into the training logs. So these are the training logs. We are going to look into SqueezeNet on Flower 102 dataset. Here you can see I trained on 15 epochs learning let 0.1, sophisticated gradient descent as the optimizer. Batch size of 32. See, the loss model accuracy has increased significantly. At the end we can see it's around 2.65%. I think so if we'll increase more, it's gonna give us more accurate results with this much small size of 1.5 MB, and the total timing took around 11 minutes and the accuracy was 4.15%. So in further iterations we can extend the training. We can train it for 50 to 100 epochs or more with more sophisticated learning rate and correct resets and converge more accurate results, especially challenging datasets like Stanford Dogs dataset. We can use additional models like GhostNet and MobileNet version 2 for comparison with version 3, and more datasets like Oxford 380 pets for another fine-grained task and Food 101 for real-world applications, and Tiny ImageNet for mid-scale evaluation. And I concluding this project is successfully compared all the state-of-the-art small model neural network across 3 diverse datasets, providing actionable insights for deployment decisions. The comparative document, code comments, and visualization of this project make this project reproducible and extensible. The key contributions is demonstrating the model selection while considering the specific deployment context. MobileNet version V3 for balancing mobile deployment, EffectNet for accuracy critical cloud application and understanding the extreme size of reducing the ShuffleNet which comes under significant accuracy trade-offs. Thank you for watching this demo. All the code and results are available in GitHub repository. So this is the GitHub repository. Thank you.